Hi, in this video we will show how one can use a left endpoint instead of right endpoint to approximate the area of the region under the graph of a given positive continuous function. Well, like before, we are assuming that f is a positive and continuous function. Well, it doesn't need to be all on its domain, just on an interval AB. Yeah. Then, like before, we can use rectangles to approximate the area, but this time, instead of having the right endpoints, we can choose left endpoint in subintervals. In other words, you do divide the interval AB into equals n equals subintervals, and for each subinterval you form a rectangle. This time, instead of using the right endpoint, we use the left endpoint and form this rectangle. For the second one, again, the left endpoint is this. We draw the vertical line up to the point you hit the graph, and then from there you have this, go up to there, and that, and so on. Well, the approximation, the computations are very similar. For example, the length of each subinterval is equal to b minus a, the length of the interval AB divided to the n equal subintervals. Then, instead of a right endpoint, which was xi on the interval I, we use the left, which will give us xi minus 1. So xi minus 1 is a plus I minus 1 delta x. Well, you can write a bit more there, I minus 1 times b minus a over n. Then the area of a subinterval, the area of the rectangle on each subinterval, on the ith subinterval, is going to be this guy, using the left endpoint. And then, you sum all these things from the first rectangle up to nth. This is the left endpoint approximation, and we use L, standing for L, n for the number of subintervals for this guy, and this is left endpoint approximation. Then we find the limit of Ln as n goes to infinity, and we just making smaller, finer rectangles, we are assuming that this will be the area under the graph of f on the interval AB. You may say, okay, wait a minute. Before you did find limit of Rn, right end point approximation, and you call that is going to be area under the graph. Now you're saying Ln is area. Which one is? Well, the theorem says if f is positive continuous function, so just continuity on AB will imply that limit of Ln and the left endpoint approximation and the limit of Rn endpoint and right endpoint approximation will be the same thing. Rn and Ln themselves will be different. Those are going to be different expressions in n, but their limit will be equal. Actually, what we have is even more. Indeed, if xi star is any point in subinterval xi minus 1 xi, so you choose any point. You don't need to choose left or right endpoints. You choose any, then the limit of the approximation using those points is going to be the same thing as limit of ln, limit of rn, and all of them are going to be area of the region under the graph of f on the interval AB. So that's what we have. If the function is continuous, you choose any point, left point, right point. In one interval, you choose midpoint. In the other one, you choose any random point from the subinterval, and then use those rectangles. This will give you the limit, not the sum itself. The limit will give you the same value. Okay, so let's, this needs a proof, which I won't be able to prove for you here. Well, it's not even part of the course. But what I can do is that we will try to see the example we did for the right endpoint, what we have for the left endpoint in this case. Okay, so remember that, recall that limit of Rn for this guy as n goes to infinity was 26/3. You can go back to other video, you will see that we found that formula. Now, delta x, actually I need to do the black. Delta x is 3 minus 1 over n, which is 2 over n. Xi minus 1 is a plus I minus 1 delta x, which is a is 1 plus I minus 1, 2 over n. And that gives us what? So the constant part I can put together, plus 2I over n. This is, well, what? N minus 2 over n plus 2I over n. Very nice. Now, delta x times f of xi minus 1 is equal to 2 over n f of that guy. So n minus 2 over n plus 2I over n squared. And from there, you right away find ln, which is 2 over n. Well, let me expand this part. N minus 2 over n squared plus 4 n minus 2 over n squared I plus 4 I squared n squared. This is ln. Well, we can go ahead and try to simplify this thing. So this will be 2n, n minus 2 over n. These are constant. There is no summing variable there, so I can put that out. And then we are summing over 1, I going from 1 to n, plus 2 over n times this piece is independent of I, so it will be 8 over n minus 2 n cubed. Sum of i's, I go from 1 to n. And the last piece is 8 over n cubed, sum of I squared. I goes from 1 to n. Now we have formula for each part of these guys. So this will be 2n minus 4 over n squared times n plus 8n minus 2 over n cubed n times n plus 1 over 2 plus h n cubed sum times n plus 1 to n plus 1 over 6. And well, this is the formula. We can simplify a little bit, like something like 2n minus 4 over n plus, here I can cancel some of these and you get 8n minus 2 n plus 1 over actually we can simplify this one also, 4 over n squared plus this is 4 over 3 n plus 1 to n plus 1 over what, n cubed. This is ln. If you check the other video, the Rn has different form. This is not equal to Rn. Ln and Rn are different. But what the theorem says is that the limit of Ln, which is going to be limit of 2n minus 4 over n plus limit of 4, let me put 4 out here, n squared minus m minus 2 over n squared, n goes to infinity, n goes to infinity, plus 4 over 3 limit of 2n cubed, oh, I could have simplified that. I could have written this one as n squared. So this will be 2n squared plus 3n plus 1 over n squared as n goes to infinity. And you either do the highest power in numerator denominator or L'Hopital rule. You get 2 plus 4 plus 8 over 3. And that gives us 18 plus 8 over 3, which is 26 over 3. And as you can see, this is the same number that we found for the limit of right endpoint approximation. And well, you see that those are, at least in this example, the same. But as the theorem says, this is true for all continuous functions. Okay.